Unit step response in time domain for a underdamped standard second order system is given by this expression, which we have derived in the previous video, and where omega d is given by this formula and theta is given by this formula. In this video we will see how does C of t look if you plot it in a graph, and we will see associated parameters of the system like rise time, peak overshoot, settling time, and steady state error. Before we simply draw the plot for this expression, let us understand how does this look if we try to plot. So to see this, we know for sinusoid, whatever values you give inside the sinusoid will take values only between -1 to +1, which means any value you substitute inside sine, the sinusoid total value can only be between -1 to 1. So in that case, for a -1 value, this expression of C of t will become 1 plus, because minus of minus, e power minus zeta omega nt over square root of 1 minus zeta square. And when sinusoid will take +1, we'll have 1 minus e power minus zeta omega nt over square root of 1 minus zeta square, which means the C of t function can only be in between these two values, where this being the upper bound, this being the lower bound. So if we try to plot this entire expression of C of t, it can be only between these two values. We can say these two expressions will be like envelopes which will be trying to guide the output expression within these two functions. Now let me try to plot C of t. Before I do that, unless I assume some values for zeta and omega n, I cannot plot the expression. So I'm going to take examples where zeta is 0.25 and omega n is 10. In this plot, for our understanding, I have plotted for the envelopes. This is for 1 plus e power minus zeta omega nt over square root of 1 minus zeta square, and this is for the lower envelope, which is 1 minus e power minus zeta omega nt over square root of 1 minus zeta square. So the green curves above and below, which are exponential ones, are for the upper bound and lower bound, and the blue curve over here, which is a constant, which is the input, and the red one over here is actually the output response we are looking for, which is C of t. And all this graph is for these values we have discussed. If you analyze this output response graph, the output response graph starts from 0 and it rises steeply to the final value that we are looking at, the reference value, which is 1, but it goes beyond the value and goes to a very high value and comes back and again reaches the reference value, which is 1. But it doesn't stay there, comes down, and it goes oscillating around the value, but the deviation from that final value keeps decreasing, and finally as t tends to infinity, this whole second term tends to 0, then the output will be 1 at t tends to infinity. So this is how the output response goes, but before it reaches the steady state, over this transitioning time where the output is changing, we have a lot of important parameters to discuss, like what is the first time it actually reaches the final value we are looking at, the 1, which we call rise time, and then it goes to the highest value throughout its response, we call the time at which it goes as peak time, and of course the output overshoots beyond the reference value, the input, by some amount, which we are going to call peak overshoot. Next, we will discuss the important parameters like rise time, peak overshoot, settling time, and steady state error. Rise time for a underdamped case is defined as the time that the output response takes to go from 0% of its final value to 100% of its final value in the first attempt. So let us look at the graph and understand this definition. So the output response starts from 0, which means 0% of the final value, and it steeply rises to a final value of 100% to its final value, which is 1 in this case, and it goes beyond this value and comes back to this value again, and it keeps doing that multiple times. So rise time, what we are defining here is the time that it takes to go from 0% to 100% of its final value in the first attempt. So this is the first attempt, this is the second attempt, third attempt. So rise time is all about finding the time that it takes to go from 0 to 100% of its final value in the first attempt. C of t at t is equal to tr. Let's say we call tr as the rise time. Then the output should be equal to 1. In that case, C of t should be 1. So this entire second term that we have, which contains the exponential and sinusoid, should be 0. So in that case, let me rewrite this, which is e power minus zeta omega nt over square root of 1 minus zeta square times sine of omega dt plus theta. This should be 0. Now we know for sure this exponential can go to 0 as t tends to infinity. But here we know the rise time in this case is a finite value, not infinity. So for a finite value of t, this exponential term can never be 0, which means there is a possibility of sine to be 0. So we can rewrite this expression saying actually the sine term can be 0, not the exponential, for a finite value of t, which is for t is equal to tr. So let me substitute tr here. So in this case, sinusoid can be 0 only if omega dtr plus theta is equal to some integer n times pi. In that case, sinusoid value can be 0. So now we know what is tr, which can be written as n pi minus theta over omega d. But now the question is, what should be n? As we said, n is an integer, so it can take 0, 1, 2 and so on values. So let us see, can it take 0? If you put 0 in this n, we'll have tr rise time is equal to minus theta over omega d. Definitely the time rise time cannot be negative, so we'll not have n is equal to 0. We can see here it took a finite positive time to come to 100% value, so we cannot have 0 as a value, so this is gone. So let us see 1. Definitely it can be 1, because we know for a zeta in between 0 and 1, the theta value can only be between 0 and 90, which means definitely this value will be positive. So for the smallest integer that we can have a real value of tr, a sensible value of tr is 1. So we can say the rise time is pi minus theta over omega d. This is the formula that we're going to use to find the rise time for an underdamped case. Now, how about the other integer values, the meaningless? No, not exactly. So if you look at the graph, there are multiple times where it actually goes through this point. So this is for corresponding n is equal to 1, and this is for n is equal to 2 and n is equal to 3 and so on. Now if you see carefully here, the n is equal to 1 point to n is equal to 3 point, if you can find the time duration between these two, we know already what this time can be, because the sinusoid oscillation frequency is omega d. So the time corresponding to omega d, the time period, will be, let me just say, t suffix d, which can be written as 2 pi by omega d. So if we can find what is the value at this point and value at this point time, if we subtract them, we should be getting exactly 2 pi by omega d. So let us see, at this point the value is pi minus theta by omega d. Now n is equal to 3, in this case we can have 3 pi minus theta by omega d. If you subtract 3 pi minus theta by omega d with pi minus theta by omega d, we get 2 pi by omega d, which represents that this time period is corresponding to the damped oscillation time period. And similarly, if we can find from here to here, this time period will also be exactly same as this time period from 1 to 3, which will be 3 to 5. So if we can find another one from 2 to 4, it will be exactly same. For our discussion and understanding, rise time is for the first time when it goes to the final value from 0%. So that is given by pi minus theta by omega t. So now this curve is given for zeta equals to 0.25 and omega n 10. So let us calculate what is the TR for this curve, which will be pi minus the theta value corresponding to zeta. Now we know what is theta. Theta is given by tan inverse of square root of 1 minus zeta square by zeta. Now when you're calculating this, don't forget to put your calculators in radians mode, because you need to calculate theta in radians. So if I calculate for 0.25, it comes out to be 1.318 for a zeta value of 0.25. So let me take it here, 318 divided by the omega d. Omega d is given by omega n, which is 10, times square root of 1 minus zeta square. Zeta is 0.25, which is 1 over 4 whole square. Now if I find the value of this, I'll get 0.188 seconds. So if you see here, if I drop this one, I get very close to 0.2, which is given here 0.188 seconds. Peak time is the time at which the output response would have reached the highest value in terms of magnitude. For the graph we have here, for values of zeta and omega n as 0.25 and 10 respectively, we have a peak value that the output response reaches is over here. And the corresponding time, if we drop this down and try to find the value, is somewhere here. So we're trying to find the time at which the output reaches the peak value. How are we going to find that? So let us see this graph. When the output is increasing, if you find the slope at any point while it is increasing, the slope would have been positive because the response is increasing as time is increasing. Whereas if you take at this point, as time is increasing, the response is decreasing. The magnitude of the response is decreasing. So the slope would be negative in this case and positive whereas here. If you see, there is a point in the middle between them where the slope would be 0. So we can define that the differentiation of the output response with respect to time at, let's say, the time Tp, at t is equal to Tp, the slope would be 0. So if we apply this condition, we can find the value of Tp for which the differentiation would be 0. So first of all, let us find the differentiation of this function c of t with respect to time. So we see here for the first term, which is constant, with respect to t, if we differentiate, the value will be 0. So we have 0 minus differentiation of this second term. So we have two terms which are functions of t. So we have a product rule that we need to apply, and if we find, we have a constant term here which we will take out, and now we need to find the differentiation of this product of exponential and sinusoid. So let me first take this exponential minus zeta omega n t times differentiation of sine, which will be cos of omega dt plus theta times omega d plus now the differentiation of exponential and multiplication of sine. So let me write it here. We have e power minus zeta omega n t. Differentiation of this will be same, but we have the exponential value which is zeta omega n. So this will be differentiation of the exponential term times sine omega dt plus theta. This value should be equal to 0 as t is substituted with Tp. So let me not substitute it now. We'll do that later. So if we can rewrite this expression, so e power minus zeta omega n t is common on both sides, and we have 1 over square root 1 minus zeta square. We can take this out. So we will be left with cos of omega dt plus theta times omega d minus zeta omega n times sine omega dt plus theta. This is equal to 0 at, of course, t is equal to Tp. Now if you remember from the root locus that we have drawn for the standard second order system, as zeta is changing, we had a semicircle like this for zeta in between 0 and 1, and we defined a theta like this. If you remember, this magnitude was omega d, and the projection over x magnitude was zeta omega n, and the magnitude of the radius of the semicircle was omega n. So if you can find the values of theta here, we knew sine theta can be written as opposite side by hypotenuse, which is omega d over omega n, and cos theta can be written as adjacent side, which is zeta omega n over hypotenuse, which is the radius of this semicircle, which is omega n. So we can see the similarity here. We have omega d, which can be written as omega n times sine theta, and zeta omega n can be written as omega n times cos theta. So in the entire expression, omega n is common. We can send it out to the other side, which is 0. So we can rewrite this entire expression as cos of omega dt plus theta times sine theta minus cos theta times sine of omega dt plus theta. This looks like sine A minus B, where A is omega dt plus theta and B is theta. So let me write this. So we can have sine of omega d Tp plus theta minus theta is equal to 0. Theta theta cancel, so we have sine of omega d Tp is equal to 0. Based on this condition, we can say omega d Tp should be equal to some integer times pi, and we can have plus or minus, but in this case, as Tp should be a positive value, as the output response here is valid for t greater than 0, so we will not be taking minus values at any case. So we will be having just plus n values, where n can take any values from 0, 1, 2, etc. so on. And of course, we can say it cannot take 0 because the time Tp is a finite value which is non-zero, at which you have the peak value. So we cannot take 0 value. So now I can say Tp, the peak time, can be written as pi by omega d, which means I assumed n is equal to 1. Now the same question, why can't we take n, 2, 3 and so on, different values? And of course, why did we get so many values? If you see the graph here, this is not the only point where the slope is 0. If you see at this point, this is also slope 0, and here also we have slope 0, here, here, and so on. It goes on. So this value at which we have the time, we called Tp. This is for n corresponding to 1 value, and this a low value is for n is equal to 2, and for this corresponding is n equals to 3, n equals to 4, and so on. Now the same logic, if we apply that from n equals to 1 to n equals to 3, if you see the time duration difference, as this damped oscillation frequency is omega d, the time period should be corresponding to that damped oscillation frequency. If you see here, without even calculating based on the n values, we know this time duration should be 2 pi by omega d, as it is oscillating with a damped oscillation frequency. So let us calculate what is at n equals to 3 the time value, which will be 3 pi by omega d, and at n equals to 1 it is pi by omega d. If you subtract, we will get 2 pi by omega d, which makes it clear that the difference between this point to this point is exactly the time duration corresponding to the damped oscillation frequency. So when a peak time is asked, we should be substituting n equals to 1, and the peak time will be pi by omega d. If it is asked what is the time at which you get the second peak, and you need to substitute n equals to 3 because you're getting the second peak. So this is low. You can calculate for different lows and different highs and so on. For this example of zeta equals to 0.25 and omega n equals to 10, let us find what is the peak time. Tp is equal to pi by omega d, which is omega n, which is 10, times square root of 1 minus zeta square, which is 1 over 16. If you find this value, this is 0.3245 seconds. if you see here, when we projected, this is somewhere close to that value, 0.32. In the previous section, we have seen that the output response goes to a peak value at a time called peak time. At that particular time, if you see how much is the output overshooting beyond the expected final value, that value is called the peak overshoot, MP. We can say its definition as MP equals to C of TP, output response magnitude at t equals to TP, minus C of infinity, the final value expected. We know C of infinity, the final value of the output response, is 1 because the exponential value tends to 0 as t is tending to infinity. So if we substitute C of infinity to 1, we can rewrite this MP as minus e power minus zeta omega nt over square root of 1 minus zeta square times sine omega dt plus theta. As the 1 at C of infinity and the 1 in C of TP gets cancelled, so we are left with this expression where t is equal to TP in both the functions. Now all we need to do is substitute the value TP, where we know TP is given by pi by omega d, and see what is MP here. So if I can rewrite, MP can be given as e power minus zeta omega n, and TP is pi by omega d. Omega d is omega n times square root of 1 minus zeta square, whole divided by square root of 1 minus zeta square, times sine of omega d times TP, where TP is pi by omega d. Both omega d's will get cancelled, so we'll have pi plus theta. So if I can rewrite this again, we have omega and omega cancel here, so we have e power minus zeta pi by square root of 1 minus zeta square divided by square root of 1 minus zeta square, times, we have a minus 1 here. Sine of pi plus theta can be written as minus sine theta. So minus minus cancel, we have sine theta. If you remember, the root locus that we have seen for the roots of the standard second order system, as zeta is between 0 and 1, it was a semicircle, and we had defined a theta value here. If you find what is that sine theta, we know it is square root of 1 minus zeta square, which is omega d over omega n. If we can substitute sine theta value here, which is square root of 1 minus zeta square, these two will exactly cancel out. So now MP finally is given by e power minus zeta pi divided by square root of 1 minus zeta square. Sometimes people are interested in another parameter which is very similar to peak overshoot, is peak percent overshoot. So peak percent overshoot is defined like this. Peak percent overshoot is C of TP, the peak value, minus the final value divided by the final value times 100%. In this case, where the final value magnitude is 1, so it doesn't make a difference between MP and percentage MP, except that multiplication of 100. So if you find this value, this will be e power minus zeta pi over square root of 1 minus zeta square times 100%. But it makes a difference when the final expected value is other than 1. We'll see the difference very clearly when you solve the follow-up problems. Let us calculate for this example where zeta is 0.25 and omega in 10, what is the MP value and peak percent overshoot. So let me substitute the values here. So we have e power minus 0.25 times pi divided by square root of 1 minus 1 by 16. We get this value to be 0.4443. If you find the peak percent overshoot, we get 44.43%. If I extend this value, it will be approximately the value we are seeing here because the graph is to scale. When does the system response settle down to a single value? Ideally, from the equation, if we substitute t, tending to infinity, then the second term would be 0. Then we'll have the output to be 1. So which means as t tends to infinity, the output response tends to become stable, or it tries to settle down to a single value. But in practice, t tending to infinity is not a value that we are interested in, because when we have two systems, we need to compare and tell which one is better compared to the other one in terms of reaching a stable value, or which one reaches faster to the final value. So in order to do that, we are going to define something called tolerance band. Most of the time we are not really interested in when does it actually go to the final value. Instead, when does it reach 95% of its final value. But in fact, we cannot simply say 95% because this output keeps changing, going up and down. So basically we should say between 95% to 105%. So which means there is a band over which the output should be within. I have represented this yellow curve above, which represents 1.05, which is 105% of the final value, and this bottom yellow curve, which is 0.95, which is 95% of the final value. Now the definition, settling time, we are defining now settling time for 5% tolerance band. It means it's a time after which the output reaches into the 5% band and stays within the band. So let us see for this graph, where does it go? When we see this graph, it enters into the band at the first time, it goes out of the band, and then it comes back in and goes out. Again comes in, goes out. But the next time when it comes in here at this point exactly, it stays within this band without going out of the band. So we can say this is the time at which the output response has come within the 5% tolerance band and will stay within this for any time greater than this. So we can say t as 5% will be this value. But now, how do we compute a formula out of this? We need to find the value of t for the c of t to be either 1.05 or 0.95. We are not going to do this computation every time. So what we can do instead is, we have this envelope graphs that we have. The upper bound, which is 1 plus e power minus zeta omega n t by square root of 1 minus zeta square, and the lower bound that we have here represented below. We can say approximately if the exponential envelopes reach within this band, we can say definitely the curve should be within the band. So what we're going to do is, we can say 1 plus the upper bound zeta omega nt over square root of 1 minus zeta square should be equal to 1.05, or similarly we can say the lower bound zeta omega nt over square root of 1 minus zeta square should be 0.95. In both the cases, we will get e power minus zeta omega nt over square root of 1 minus zeta square to be 0.05. All we need to do is find the value of t for which we will get this to be approximately 0.05. Now I'm going to do some approximation here. I'll say e power minus zeta omega nt should be equal to 0.05. Let us find what is the TS for 5% settling band. We can find e power minus 3 will be equal to 0.049, which is approximately 0.05, which means the exponential here should be 3. The value should be 3. We can say zeta omega n times TS should be 3. We can also say TS is equal to 3 by zeta omega n. Now we can say this constant that we have here, 3 times 1 over zeta omega n, we'll call this the time constant. So let me write it here. TS 5% is equal to 3 times the time constant, which is 3 over zeta omega n. So this is the formula for settling time for 5% tolerance band. But now, definitely if you use this formula to compute, it's not going to be the exact time at which the output response would have been in the 5% tolerance band and stays within after which. It's not going to be, because let us see this example here. This output response has reached TS 5% here, to be precise. But we are trying to calculate the formula based on the envelope curves. If you see envelope curves, these envelopes have intersected with this 1.05, the upper bound, and the lower bound with 0.95 at a different time. So the time that we are getting from this formula is not exactly equal to the real 5% settling time. But still, for practical purposes, when we do computations, this is a decent formula to use to find the 5% settling band. And similarly, we have a 2% settling band, TS 2%. If you can compute, the exponential should be e power minus 4 to get 0.02 approximately. So we will get 2% settling time is 4 time constants, which is 4 over zeta omega n. So these are the formulas for 5% settling time and 2% settling time. We know from the time response graph that we have seen that the output reaches to the final value as t tends to infinity, which means that there is no error whatsoever in the output response with respect to the expected input value. But to have a model here to represent and find out the values consistently, I'm representing this standard second order system in a unity negative feedback loop where output is C of s, input R of s, and the difference between the input signal to the output signal is the error signal, in this case E of s. So we can say E of s can be written as R of s minus C of s, and let me take this transfer function as G of s, and H of s is 1, so I can write this again as R of s minus E of s times G of s. We can find E of s 1 plus G of s is equal to R of s. Now we know what is error signal, which is R of s over 1 plus G of s. Once we know the error signal in terms of s domain, to find the final value of the error, we can find limit t tends to infinity for E of t in time domain will be also equal to, applying the final value theorem, we can say limit s tends to 0 s times E of s. Now let's apply the condition here where limit s tends to 0 s times R of s. In our case, we have been seeing the output response of the system for unit step input. So in that case, for unit step, R of s is 1 over s divided by 1 plus G of s. G of s here is omega n square over s times s plus 2 zeta omega n. Now s cancel, and if I apply s tends to 0, we have numerator 1 over 1 plus, if you apply limit s tends to 0 for this term, we will have infinity because we have 1 over s. Then the error would be 0. And from the graph, we knew already that it is 0. But in case for a different kind of input that we apply, let's say a ramp input, you know how to calculate the steady state error by using this model. You can substitute R of s as 1 over s square and try to calculate what's the error. For a unit step input, for a standard second order system, for underdamped case or overdamped case or even critically damped case, the steady state error will be 0. But for undamped case, we cannot say the error is 0. Now let me apply this case to underdamped case where limit s tends to 0, s times R of s is 1 over s for unit step input, 1 plus omega n square over s times s plus 2 zeta omega n. For undamped case, zeta is 0. If we substitute, we'll have just s square. If we rewrite this, we'll have limit s tends to 0, s square over s square plus omega n square. Now we cannot use the final value theorem for cases where the system is marginally stable, in the sense it has roots on j omega axis. We cannot use the final value theorem. So what should we do instead? We know the time response of the system for undamped case where the input was at 1 and the output response was like this. The peak value was 2, which was repeating every time, and it goes all the way to 0. This output never settles down, which means if I can take the error will be at least, let me take it here, R of t minus C of t. If you take, we can never say what is the value because it keeps changing. So we can only say the range within which the error can be. And if you see, R of t is always 1 and C of t can have a value of 2 or 0. If I can substitute here, we can have for r of t1 and C of t2, we can have -1. When r of t is 1, C of t is 0, at an extreme value, we can have 1. Which means the error will be in a range from -1 to 1 for undamped case. So if I can summarize, for zeta greater than 0, where we have underdamped, critically damped, and overdamped case, the steady state error is 0. Whereas for zeta equals to 0, the steady state error basically lies between -1 to 1. We cannot specifically say what's the value.